today. Matthew joins us from Chicago, but he's at the Kavli IPMU in Tokyo. And he'll be talking to us about Chern-Simons invariants from ensemble averages. Matthew, thank you.
Okay, well, thanks for the invitation. This is based on a paper from earlier this month with some collaborators from IPMU, Ashwin Kumar, Kidambi, Lidam, and Yamazaki. So here's the outline of the talk. I'll start with the motivation, which comes from this recent proposal that sometimes we need to consider holography with ensembles of boundary CFTs, not with CFTs themselves. And then I'll construct the model, which is based on a free boson CFT associated to a lattice. In the third part, I'll consider the ensemble average of this model, and I'll discuss how this is related to something called the Sigo theorem. And then I'll consider the bulk theory, which I'll show is a Chern-Simons theory associated to a lattice. In the next section, I'll discuss the positive definite case, a positive definite lattice, which has to be treated separately. And then I'll move on to spin CFTs, fermionic CFTs, and the duality to spin Chern-Simons theory. And finally, I'll conclude with some comments on the duality before averaging, and I'll speculate that this is related to adding a Maxwell term to the Chern-Simons theory. Okay, so that's where we're going. So let's start with the presentation.
Didn't get that. Could you try again?
Siri, but hopefully she won't talk anymore. So the conventional statement of holographic duality is that a CFT is dual to a bulk gravity theory in ADS. So the standard statement is that we can compute the bulk partition function with fields that approach some source J at the boundary, and then this is equal to the boundary partition function with source J for the field. So that's the standard statement. But recently, it's been suggested that sometimes you have to average ZCFT over a suitable ensemble. So there are some examples in lower dimensions. So the first example from Sada et al. And Stanford and Witten is this duality between JT gravity and a matrix ensemble. So JT gravity is a two-dimensional theory of gravity, and it's dual to this matrix ensemble on the boundary. So here, the betas are the lengths of circles on the asymptotic boundary of the bulk, and the boundary partition function, or sorry, the bulk partition function is equal to the ensemble average of this product of traces on the boundary over the matrix ensemble. So that's an example in 2 dimensions. In the context of 3-dimensional gravity, it's not as clear, but there's an indirect argument that possibly it's also dual to an ensemble average. So this is due to Kotler and Jensen. So you can compute the path integral with 2 torus boundaries in the bulk. So we have 2 disconnected tori, and they're connected by some geometry. And so this is the partition function on T2 cross an interval, and that has an interpretation as the product, the connected correlator of 2 partition functions on the boundary. So the right-hand side is like a Euclidean wormhole geometry, and if there wasn't an ensemble, then there would be no connected piece to this correlator, because the partition function would just factorize. And so the fact that this is non-zero suggests that there is an ensemble in this case as well. So that's kind of an indirect argument. But a simple toy example where everything can be worked out exactly was discussed by Maloney and Witten and Afghani-Jetty et al. So instead of Einstein gravity in the bulk, they consider Chern-Simons theory with a gauge group U1 to the 2p, where p is an integer. And in this case, the boundary ensemble is the Noreen moduli space MP. So this is familiar from string theory, but it's the moduli space of CFTs with p compact scalar fields. And in this case, the average partition function can be computed using something called the Sigo theorem. And they needed a special case of this theorem, but I'll have to use the more general case. And this theorem relates averaged theta functions to Eisenstein series. So the theta function is something that counts properties of a lattice and is averaged over a moduli space, MP. And that's equal to something called the Eisenstein series. So this is something that has singularities at all the rational points of the upper half plane on the real line. So the right hand side has the interpretation as the Chern-Simons partition function summed over all geometries with the torus boundary. And so this is a kind of holographic duality where you have to average over the moduli space, and then you get Chern-Simons partition functions. So that's the basic example. In this talk, I'll consider a more general ensemble average. In this case, we can consider a CFT, a wider class of CFTs that are defined by a general integral lattice. And we'll see that, again, it's the partition function is reproduced by by Chern-Simons theory, but now you need to evaluate the partition function on a length space. Okay, so that's the motivation. Any questions about that? Okay, so let's construct the model. So we're interested in CFTs that are constructed out of free bosons, and in particular, I want P left moving and Q right moving bosons. And so we have some abstract set of vertex operators, and we want to specify which ones are allowed in the theory. So the vertex operators are e to the ikx. So there's left moving and right moving momenta here. And to define the theory, we need to choose some subset of these vertex operators to include. The theory has to be closed under the OPE. So in fact, the allowed values of K form a lattice, lambda. So we also want the vertex operators to have integer spin so that they're bosons, although I'll consider the fermionic case later. So for them to have integer spin, we need K left squared minus K right squared to be an even integer. So what this means is that we have an even quadratic form, and it has signature P comma Q. So it's defined by this formula, Q of KL and KR is KL squared minus KR squared. Now we also have another function in this theory because we have a stress tensor. We have a Hamiltonian, and this does not need to be an integer. It takes the form H is KL squared plus KR squared. So if we have a lattice lambda, there's many ways of embedding the lattice with quadratic form Q into a space with a signature P comma Q. To see this, suppose that M preserves Q under transposition, which means that M transpose QM equals Q. And Q is the Gram matrix for lambda. So it's the matrix of inner products. So now we can, so if we have such a lattice lambda, we can rotate lambda to M lambda to get an equally good embedding of the lattice into RP comma Q. However, if M also preserves the Hamiltonian, then it's a symmetry of the theory. And so that's not a separate point in moduli space. And also there's a discrete group of matrices that just permutes the points of the lattice. And so we want to mod out by both of these subgroups. And so the moduli space is P comma Q divided by the group that preserves the Hamiltonian, which is OP times OQ. And then there's also a discrete subgroup, which is OPQ with valued in Z. So this is the full moduli space. It's called the Narain moduli space, and it has dimension P times Q. So the simplest example would be a free boson on the circle. So here P left is N over 2R plus W times R. N is the KK momentum, and W is the winding number. And P right is the same thing, but with W flipped. And then this quadratic form Q is 2 times N times W. So the Q is independent of the moduli space. So the radius R parameterizes the moduli space. And more generally in toroidal compactification, the moduli space is parameterized by the internal metric G and the B field. And if we're in a heterotic theory, we also have a gauge field. So now we can compute the partition function on the torus at some point in the moduli space. And it's equal to a theta function over eta functions. So the theta function is just the sum over the points in the lattice of e to the I p left squared tau minus I pi p right squared tau bar. So that's the standard formula, q to the p left squared, q bar to the p right squared. So in general, this theory is not modular invariant. So there's some representation of the modular group, but it's not trivial. And to derive the form of the modular transformations, I'll define a shifted theta function. So here we shift L by H in this summand, and this defines the theta function theta QH. So here H is valued in the dual lattice model lattice. The dual lattice is defined by all x such that Q of x with L is an integer for all L in the lattice. So now I can compute the action of the modular group. So the T transformation is actually diagonal in the H space. It just gives a phase. And then the S transformation acts as a Fourier transform in the H space. So the simplest example would be a self-dual lattice. So in that case, lambda star is actually equal to lambda, and also the determinant of Q equals 1. So for instance, a compact boson is a self-dual lattice. In this case, the theory is modular invariant from these formulas when P minus Q is 24 times N for some integer N. So note that the representation of the modular group is actually independent of the points in moduli space. namely these transformations don't depend on the moduli. So what this means is that if there's actually a holographic duality after the averaging, there should be a bulk interpretation of these modular transformations since they survive the average. So we'll see that indeed this is the case in Chern-Simons theory. These modular transformations act on the Hilbert space. Okay, any questions about the model? Okay, so now let's consider the ensemble average. So we have a moduli space, we have a partition function, and we want to take the average over the moduli space with some harm measure, which is uniquely determined by the moduli space. So this integral was actually computed by Sigo, and as long as p plus q is greater than 4, this integral converges, and the answer is given by a delta function when h is in the lattice, plus a sum over singularities at tau equals minus d over c. So here c and d are co-prime integers, and there's some singularities at each of these rational numbers, d over c. The coefficient of the singularity is given by a quadratic Gauss sum, gamma q of c and d, and it takes this form. So it's a sum over lambda mod c lambda of some phases. So first, let's see what happens in the case where we have p equals q. So this is toroidal compactification, and also a self-dual lattice. So for this case, gamma is actually 1. These gammas are 1, so that the average theta function is equal to just the ordinary Eisenstein series, E p over 2, p over 2. So this is a non-holomorphic Eisenstein series, as opposed to the holomorphic Eisenstein series that might be familiar. But this was the case that was considered in the average partition function of the compact boson. But more generally, we can think of this average theta function as a generalized Eisenstein series EQ comma H. So now let's give a proof of the Siegel-Weyl theorem. This proof is much simpler than Siegel's original proof. So what he did was actually do the integral, but we can be a little trickier and give a simpler proof. So these theta functions, as I described before, are not modular invariant, but they are invariant under a subgroup of the transformations. So this is given by gamma of n, and it's all elements of SL2Z such that A and D are congruent to 1 mod n, and B or C are congruent to 0 mod n. So n is the smallest integer such that n q inverse is an even quadratic form. It's called the level of the quadratic form q. And so therefore, the theta function is a modular form on the upper half plane, quotiented out by gamma of n. So this quotient has cusps at the images of tau equals I infinity under the quotient of PSL2Z by gamma of n. And we can just compute the behavior of the theta function near the cusp by just using the transformation law. And we get that it matches the behavior of the Eisenstein series at the cusps. So just to recall, we had this formula for the Eisenstein series, and the behavior at the cusp is equal to the behavior of the theta function. Okay, so the next step is to show that both of these functions satisfy the same differential equation. So this can be done pretty easily, although I won't show the details here. And so they're both zero, or sorry, they're both eigenfunctions of the Laplace operator with the same eigenvalue. So the Laplacian is defined by this formula. Minus tau 2 squared partial 1 squared plus partial 2 squared plus this this extra term proportional to k for a weight k form. So now we need a bound on the eigenvalue of such an eigenfunction. If the eigenfunction is normalizable, then we can form this integral, and it converges. And by integrating by parts, we get this that this is greater than 0. So what this means is that the minimum eigenvalue for a normalizable eigenfunction is equal to k over 2 times 1 minus k over 2. So I just showed that the Eisenstein series and the theta function have the same behavior at the cusps, and so that their difference is actually normalizable on the full surface. And because of this formula, their eigenvalue is less than the minimum allowed eigenvalue, and so this function must vanish. And so that means that E is equal to the theta function, the averaged theta function. I should also say that for Q equals 0, for the positive definite case, lambda is actually equal to the minimum eigenvalue, and so this argument does not work. So I'll have to treat that separately later. Okay, so that proves the Sigo-Weil theorem, and now we want to consider the bulk description. Are there any questions about this analysis? Okay, so now let's discuss the matching to Chern-Simons theory. So I showed before that the average partition function is equal to E over the eta functions, and we would like to find a bulk interpretation of this partition function. So first we can match the symmetries. On the boundary, we have a U1 to the P plus Q symmetry, which is just shifts of the field. So the bulk should also have a U1 to the P plus Q gauge symmetry. And the other piece of data that we have is this integral quadratic form Q. In Chern-Simons theory, the level matrix is quantized to get a consistent theory. And so a natural guess is that the bulk theory is a U1 to the P plus Q Chern-Simons theory, and its action is just given by this integral quadratic form Q. So that's the kinetic term coefficient. And so this is the guess for the action. And we also have this parameter H, which was valued in the dual lattice Montel lattice. And it'll turn out that H will label the states of the Chern-Simons theory. And the partition function ZQH will correspond to computing the partition function in the bulk with the Wilson line wrapping a non-contractible cycle in the bulk. So now we can try to match the partition function. We need to sum over all geometries that asymptotically approach the torus on the boundary. So the relevant geometries are well known. They were classified by Maloney and Witten. And I'll call them MCD. and they're quotients of ADS3 by a discrete group of isometries. And each MCD is labeled by an element of PSL2Z. So for example, M01 is ordinary thermal ADS, and M10 is the BTZ black hole. So now let's compute the partition functions. So for thermal ADS3, the contribution is given by the U1 vacuum character for P left movers and Q right movers. So that's just equal to 1 over eta to the P times 1 over eta bar to the Q. Okay, so that's pretty simple. And to get the contribution from other geometries, we just apply a modular transformation. And as I said before, the states in the Hilbert space are obtained by inserting a Wilson line along the non-contractible cycle. And so the modular group acts on this Hilbert space, and acting with a modular transformation, U of G, gives the contribution from MC, comma D. And so this is the matrix element of this group element acting on the vacuum. And finally, we need to sum over all G to get the partition function. But actually, there's an ambiguity in associating a group element to MCD, and this is given by gamma infinity, which is generated by tau goes to tau plus 1. And so that's, yeah, so that corresponds to the framing, anomaly transformation. Tau goes to tau plus 1. And so we have to quotient out by that subgroup. And so we just get this final sum. So now we want to understand the numerator a little bit. So the numerator can be obtained by taking a solid torus corresponding to the state 0, acting with a group element G, and then gluing to another solid torus with a Wilson line inserted. And so this closed geometry that you form by gluing these two solid tori is called a lens space, and it's a quotient of the 3-sphere by this transformation on the space. And so this full matrix element is the partition function on a lens space. And this was computed by Jeffrey in the 90s. It's equal to this quadratic Gauss sum gamma that I had before, times this other piece where phi is the Rademacher function on G, and so this is an overall phase that's that multiplies the quadratic Gauss sum. Okay, so at first it looks like there's an anomaly under gamma infinity because this Rademacher piece transforms under gamma infinity. But actually this cancels the transformation of the eta functions in this denominator because they also transform according to the Rademacher function. And so finally, we're left with this sum that we had before, and it's exactly the Eisenstein series over these eta functions. And so the partition function in the bulk geometry reproduces the ensemble average of the boundary theory. So there's kind of a subtlety here, which is we only consider the fluctuations around the vacuum state. But in U1 Chern-Simons theory, we should really sum over the large gauge transformations to get a gauge invariant state. But this does not give the right answer in our case. So it seems like this theory is only really makes sense perturbatively, and we should try to understand the non-perturbative definition a bit better. Okay, so that was the matching of the bulk to the boundary. Any questions at this point? Okay, so now I said I need to treat the positive definite case differently. So this involves some actual number theory. I need some definitions. I'll say that Q and Q prime are equivalent in a field F if there exists some matrix such that they're equivalent under transposition. Q and Q prime are in the same class if they're equivalent in Z, and Q and Q prime are in the same genus if they're equivalent in the real numbers and in the p-adic numbers for all primes P. The theta function is invariant if we apply a GL2Z transformation, and so the theta function only depends on the class of Q. Sorry, that's a typo. It should say the theta function only depends on. Sorry. No, that's right. The theta function only depends on the class of Q. Sorry, and so we can average the theta function over a given genus, and so we have a certain number of classes in the genus, and we can consider this ensemble average. So here, this denominator here is the order of the orthogonal group of Q and Z, and so it's just weighting the theta function by the order of its automorphism group. And the Sigo theorem in this case says that in this ensemble average, the theta function averaged is equal to the Eisenstein series. Now it's not as easy to prove it using our techniques, but it was proven by Sigo, for example, in the 30s. So this concept of the genus is actually unique to the positive definite case, because for indefinite forms, there's only one class in a given genus. So for example, when P equals 24, we have to average over the 24 even self-dual lattices, which are called the Niemeyer lattices. And so this duality it kind of tells us the average properties of these Niemeyer lattices, for example. Actually, there's a more general theorem in this positive definite case. So I'll quickly describe that. So if a polynomial satisfies Qij dij p equals 0, then it's said to be spherical. Also, if p is spherical, then p of dx is a primary operator. So that's a simple calculation. And then you can show that the one-point function on the torus of this operator dx is equal to this modified theta function where you insert this polynomial p of l. So in this language, there's a theorem by Waldsberger, and in this language, it says that you can take the ensemble average of these correlation functions. And his theorem says something very specific about some specific primary operators. And in terms of Heck operators, Gegenbauer polynomials, and some function called Cohen's function. But at whatever these functions are, he computes the average of these correlation functions over the ensemble. And it would be interesting to understand the bulk interpretation of this, but we don't understand this yet. Okay. So now let me discuss spin CFTs and spin Chern-Simons theory. So up until now, I've only considered even Q, and so the spin is an integer. Now I want to consider odd Q and allow for odd lattices. And what this means is that the spin of these vertex operators can actually be half integral, and so we have fermions. Even though they're constructed out of bosons, they anti-commute with each other. So to motivate the partition function, we call the partition function for a free fermion, and in this case we have 4 spin structures, and they're labeled by 2 integers, epsilon I, which take values in 0 and 1. So here, epsilon 1 labels the periodicity on the spatial circle, and so that's shifted in the sum, and epsilon 2 labels the periodicity on the thermal circle. And so on the thermal circle, we insert an operator -1 to the f, and that corresponds to this -1 to the epsilon 2 L squared there. And then on the thermal circle, on the spatial circle, we have either R sector or NS sector, and that corresponds to this shift in the sum. So in this case, we can again compute the partition function, and it's a generalization of the free fermion. So in our case, we have some vertex operators, e to the ikx, and we want to sum over all of them. And we have some spin structures, and so to insert the thermal periodicity, we put in this factor -1 to the epsilon 2 times the inner product of W with L. So I'll define W in a second. And then to consider the effects of the spatial periodicity, we shift the sum by W over 2. So here W is called the Wu class. It's defined by this formula. The inner product of W with L gives the Q of L with itself mod 2. So in other words, if L is a fermion, then Q of L with itself is 1 mod 2. And so W with L, the inner product of W with L tells you whether L is a fermion or a boson. And so what this means is that -1 to the W with L is equal to -1 to the F. We can actually solve for W in terms of Q. Its components are equal to the diagonal components of Q. And then the dependence on epsilon 1 comes into play because e to the IW dot x equals 2 over 2 is the spin field. This makes fermions antiperiodic on the spatial circle. This is analogous to, in the free fermion case, we have a spin field in the bosonized description that's e to the I x left over 2, and this makes the fermions antiperiodic on the spatial circle. So that explains the shift in this sum. Okay, so now let's take the ensemble average. So to do this, we need to use a trick. And first, I'll consider the trivial spin structure. So in this case, we have this formula, for the theta function, and all I do is to multiply p left squared and p right squared by 2, and to divide a tau by 2 and tau by 2. And if I use this trick, then I see that the theta function is equal to the theta function for a quadratic form 2 times q, evaluated at tau over 2. So now 2 times q is an even quadratic form. And so we can use the ordinary Sigo theorem on the right-hand side. And so it follows that the averaged theta function with trivial spin structure is equal to the Eisenstein series for 2q evaluated at tau over 2. So this can be simplified a bit, and it's exactly the Eisenstein series from before, but there's some congruence conditions on C and D, namely C times D has to be even. Okay, so that gives the trivial spin structures, sorry. And now we need to know the other ones, but that's easy because we could just act with the modular group on the Eisenstein series. So I'll take the self-dual case for simplicity. Then you can show that the modular group acts in this way on the theta functions. So for instance, the T transformation permutes the 0-0 structure with the 0-1 structure, and it leaves the 1-0 structure invariant. And the S transformation permutes the 0-1 structure and the 1-0 structure, and it leaves the 0-0 structure invariant. Okay. So therefore, these three spin structures form a triplet under the modular group. And we can compute the average theta functions for this triplet by just transforming the trivial Eisenstein series, the 0-0 Eisenstein series. And we get similar formulas from before. Again, we have some congruency conditions on C and D. So that gives the triplet Eisenstein series. And finally, the last theta function is actually a singlet under the modular group. And you can show that this implies that it actually vanishes at all the cusps. And so when we take its average, we actually get 0. Okay, so that was the boundary description. Now let's consider the bulk. So in this case, we need to review spin Chern-Simons theory. So in the usual Chern-Simons case, you can write the action in terms of a bounding four manifold. So here n is the boundary of n, and we have the action, and you can write it as the integral over this four manifold n of q of f with f. However, we need to check that this doesn't depend on the choice of the four manifold n, and the difference between the action for two different four manifolds is equal to the integral over the closed four manifold that's formed by gluing these two four manifolds along their boundary. And so that's equal to this delta S. So therefore, if Q is even, you can show that the delta S is equal to 2 pi I times some integer. And so each of the minus delta S equals 1. And so what this means is that it's independent of the choice of n, because the path integral just involves each of the minus delta S. So that was true if Q is even, but now let's assume that Q is odd. So it has some odd values. but let's also suppose that the manifold N has a spin structure that's compatible with M. It turns out that in this case, the integral of this function is still an integer, and so therefore we can define a spin Chern-Simons theory for odd Q also, but now it will depend on the choice of the spin structure. Okay, so now in this case, we can express the average partition functions in terms of the partition functions of spin Chern-Simons theory on lens spaces. So here, these states are labeled by, again, these integers epsilon1 and epsilon2, and the numerator is the sum of two partition functions of spin Chern-Simons theory. So for instance, for the thermal ADS contribution, G, this group element G is equal to 1. And so only two of the spin structures are non-zero. And from this formula, we can actually derive the congruence conditions on C and D. So for instance, if C and D are both odd, then up to the framing anomaly, we have this group element is equal to S times T times S mod 2. So what this means is that these two terms in the numerator actually vanish, and so this the summand of E00 actually vanishes, and so that's consistent with what we had before, which is that C times D had to be even. So you can actually check this formula in some special cases, but you have to use some generalized Gauss reciprocity due to de Loop and Turayev. Okay, so that was the spin case. Any questions about that?
Yeah, sorry. Can you just remind me what is Q of A and F? Is it the standard ADA plus 2/3 A cubed?
Yeah, but this is a abelian, so yeah.
Oh, I see. So just ADA or
Yeah.
AF, A with F.
Yeah, I think you can also consider the non-abelian case, but yeah, here it's just abelian. Yeah.
Okay. And so Q of FF would be F wedge F.
Yeah, but with this additional Q index. I mean, it depends on the quadratic form Q. Yeah.
Okay, but in your formula, they're the same quadratic form, or?
Yeah, the same one. Yeah.
Okay, good. Cool, thanks.
Great. Okay, so now I'm almost done, but I just want to consider a quick discussion of the duality before averaging. So so far I've given evidence for the duality after the average, and this theory doesn't depend on the moduli because we are averaged over them. But you might hope that there's some fine-grained duality that holds before the ensemble average. And so to look for this duality, let's just include a Maxwell term in the Chern-Simons action. And so that's this first term here. And there's some matrix lambda ij, and it's proportional to 1 over E. So E is dimensional, so its effect should go away in the IR. But actually, it turns out that the effects of E affect the quantization conditions for the gauge field in the IR. And so this matrix lambda will actually give some new effects in the IR. And what you get is that for appropriate boundary conditions on the field, in fact, the partition function of this theory exactly matches the partition function of the boundary theory not averaged over the moduli. sorry, and there's some relation between the matrix lambda and the moduli theory. It's given by this formula. So what this suggests is that Maxwell Chern-Simons theory is dual to the boundary theory before averaging over the moduli space. After averaging, we have some coarse-grained description of this duality. So a kind of interesting feature of this duality before averaging is that we actually don't have to sum over the geometries. We don't have these MCD geometries. We can just evaluate the partition function over on pure thermal ADS. So what this suggests is that maybe this the sum over geometries is an artifact of some coarse-grained description of the theory. So this was also discussed by Eberhardt in the context of string theory. He showed that in string theory you don't need to explicitly sum over the geometries because it's already built in to the microscopic theory. So it seems like this might be a more general principle that the sum over bulk geometries might be an emergent property of the theory. Okay, so let me wrap up. So I've discussed a duality between free boson theories that are associated to integral lattices and Chern-Simons theory. So there's a couple interesting things that we're working on. So one thing that would be interesting would be to find the bulk dual of a CFT that's not defined by integral lattices, but by rational lattices. So what this means is that the spin is rational. So there are actually parafermions on the boundary. So I can make one comment. So suppose that n times q is even. So q is a rational matrix, but there's always some integer n such that n times q is even. Well, then we can apply the same trick as for spin CFTs to compute the ensemble average. We just multiply q by n and multiply tau by 1 over n. And so that gives the average partition function of this theory. And so this leads to some representation of the modular group. But it's not clear what the bulk interpretation is because there's no such thing as paraspin Chern-Simons theory, at least not that I know of. So it would be interesting to understand if there is a bulk description. Another question is orbifolds. So we have a symmetry A to minus A, and you can try to gauge that symmetry. And in this case, the 4-point function of twist operators on the sphere is expressed in terms of a sum over rational tangles in the bulk. So you have some vortices in the bulk, and they're tangled up, and you have to sum over all the rational configurations. So we're trying to understand the effects of general lattices in this context. It's possible that the Eisenstein series should contain invariants of rational tangles that are analogous to the lens space invariants that I considered here. So that would be an interesting connection to number theory. Okay, so I'll stop there for questions. Thank you.
Thanks, Matthew. That was a really nice talk. So let's ask, are there any questions for Matthew? If not, I have some questions. So the idea is, so I kind of got interested in this area after listening to Steve Schenker a couple of years ago. Say how there's really something remarkable going on, because you have, you know, the folklore in ADS-CFT is you have a unique ADS dual to a unique CFT. And yet all the lessons that we're learning from JT gravity seems to be pointing to the idea that to get the bulk dual, in this case, two-dimensional JT gravity, you've got to average over an ensemble of SYK models. And then, of course, you know, there was this Narayana ensemble lurking in the background for many, many years, and it was realized by, I guess, Maloney and Witten, that you could take an average of an ensemble average of these Narayana models, and you're getting Chern-Simons in 3D. And you've just, you know, you've extended that quite nicely. So you know, somebody asked in the audience, is the idea then that, you know, to see even ADS5 cross S5, you've kind of got to take some ensemble average of n equals 4 super angles in some sense? Is that kind of the?
No, I think we know that I think we think that that's a good duality, right? So yeah, so it's a good question. When do you need to consider an ensemble average, and when do you not?
Right.
But I mean, in that case, I don't think we have a candidate for a moduli space. Let's see. We don't have I don't think we have exactly marginal operators that preserve all the supersymmetry. So unless I'm mistaken. So I don't think there's a candidate for an ensemble there. Oops, sorry. I think someone's muted.
You could sharpen the question then and ask, you know, what you've just asked, which is, when do you have a unique CFT dual, and when do you need to do an ensemble average?
Right.
In all cases, you're seeing, you know, you're seeing a unique bulk, right? Yeah. But in some cases, you've got to take an average over a large number of dual CFTs, and in some cases, you get a unique one.
Yeah, I guess I would maybe advocate for the idea that there's always some underlying duality without an ensemble, and the ensemble description is some kind of coarse-grained description of the underlying duality in terms of the microscopic theory. So right. That's kind of what I would hope. But
right.
Yeah.
So then let me ask another question. So your statement here is that if I take a free boson on a lattice and I do an ensemble average over the free boson on the lattice, I'll get 3D Chern-Simons, right?
Yeah.
I think this is true so I know that the free boson, the continuum free boson is dual by Bose-Fermi duality to a free fermion. Mm-hmm. I'm not sure if that's strictly true on the lattice.
But sorry, but it's a different lattice, right?
That's right. So you've got to dualize the lattice, right? You've got to take some.
But sorry, but it's not a lattice. It's not a lattice on the world sheet. It's a lattice in the K space, right? It's a lattice of vertex operators.
Which one?
So the one I'm considering is a lattice. It's not like we have a field theory on a lattice. We have a field theory whose vertex operators are valued in a lattice, right? So
yeah. Okay. Yeah. So where I'm getting at is, you know, so the Bose-Fermi duality in that case is just one example of a duality like this, right? So I can in principle dualize, in a lattice sense, this free boson theory as well, right? I'll get a free boson on a dual lattice. Yeah. Is there any? So firstly, is the physics of that the same as the original one that you're considering? And secondly, if you take an ensemble average over the dual theory, would you get the same Chern-Simons?
Let's see if we can think of a simple example. So So can we consider the compact boson, so the even self-dual lattice?
Sorry, say that again.
Would the compact boson be a suitable example? So
Yeah, right.
okay, so
There you lattice self-dual, right?
oh, you mean dualize the lattice? Yeah. Yeah. No, I don't think it's the same theory. I mean, the dual lattice is much bigger in general. So yeah, I
Sorry,
don't.
can you say that again?
The dual lattice is much bigger, so I think it's not quite the same theory. But
Okay.
yeah.
Okay. All right.
Yeah, I would need to think. Yeah, I'm not sure.
I had another question about the Maxwell Chern-Simons. No, I can't. It's escaped me. I'll send you an email when I can remember.
Sure.
It had to do with duality there as well, but I can't remember exactly now.
Yeah, that's kind of a weird case because it's barely even holography. It's like what's it called? Bulk edge duality in condensed matter physics.
Condensed matter, yeah.
No, there's no real gravity going on. So it's because there's no sum over geometry. So yeah. It's kind of an odd situation.
Right. So that right. So strictly that's not an example of a gauge gravity duality.
But then you average, and you get a gauge gravity duality.
But you average over what in that case?
Oh, over the moduli. So over the Maxwell terms. So the Maxwell terms are they parameterize the Narain moduli space, and once you average, you get the ordinary duality I consider in the paper with no Maxwell term, and in that case, it indeed has a sum over the bulk geometry. So.
I'm confused now. So the Maxwell Chern-Simons that you consider is in the bulk, right? It's in
Yes.
Right?
Yeah.
So let me see if I understand. So you start off with the Maxwell Chern-Simons. So what was you made a statement about the IR. So if I send E to infinity, there's compensating terms that come from the lambda. There's some compensation that comes from the lambda? So normally I would have that lambda matrix equal to 1, and I'd have dA wedge star dA, and then if I take the IR limit and send it.
Sorry, let me
share
the. I'm just going to share my screen again. How do I do this?
I can see your screen.
Sorry. Yeah. So normally E would be infinity, and lambda wouldn't be there.
Yep.
But it turns out that lambda actually affects the quantization of the theory. So
I see.
Yeah.
I see. So you have to keep it in that case.
Yeah.
And then so what happens? So M is 3D. And what am I averaging over?
So over the matrix lambda. So
okay.
This is a positive. So you might imagine in string theory we reduce and we get some moduli matrix, and we have to average over those moduli.
Mm-hmm.
And so in the microscopic theory, we would have some fixed modulus, and then we would coarse grain, we would average over the moduli, and then we would get this the sum over geometries.
Mm-hmm.
Yeah.
Mm-hmm. Okay, I see. So you average over lambda.
Yeah.
And so then your path integral gives you 3D gravity essentially, right?
Yeah.
What's the gauge group for A?
U1 to the P plus Q. So it's not 3D gravity, and
it's 3D Chern-Simons. It's a compact gauge group, right?
Yeah, but it has this feature of 3D gravity that we sum over geometries. So that's not.
I mean, even after the averaging, you still have a compact group?
Yeah.
Well, that's interesting.
Yeah.
Huh. Interesting.
Yeah.
Well, that's very cool. Well, thank you. That was a really nice talk.
Sure, happy to do it.
So let me stop. Let me ask again. Are there any questions for Matthew? Not. Thank you again, Matthew. That was a really nice talk.
Thanks for having me.
Thanks for speaking.